So those of you who have done some quantum mechanics, you have seen this derivation before. But even if you haven't seen the angular momentum algebra being derived, you probably have seen a treatment of the simple harmonic oscillator using the ladder operators. And what we are doing here is very similar to that construction. Okay, so let's now recall what the rank of SU2 is. Does anyone recall what the rank of SU2 is?
One.
Yes, one. Right. So Fiza answered this last time too. Was that you, Fiza?
Yes, sir.
Yeah. So she answered it because SU2 is, you know, the Lie algebra of SU2 is the same as the Lie algebra of SO3, and you know, and we know. So there are two ways of looking at the rank, right? One is we know that the Lie algebra of SO3 you know, involves rotation in the 1-2 plane and the 2-3 plane and the 3-1 plane. And there's really only one pair of plane that we can choose independently of these three planes. That's one way of looking at it. The other way of looking at it is that, you know, when we were doing the analysis of SUN, remember that the generators of SUN are all Hermitian as well as traceless, right? And we constructed, for SUN, we could construct n-1 diagonal, you know, traceless and Hermitian matrices, okay? And those are so they are, and they all commute amongst themselves, and they don't commute with the other traceless Hermitian matrices. And in this case, that n so becomes 2, so there's only one rank. Sorry, Saif, you were also answering it, but you probably wanted to answer it in a different way. Do you want to give your answer?
I think you've already said what I was going to say, so it's fine.
Okay. So yeah, so there are two ways of looking at SU2. Okay. So so we can choose. We have a choice about which one we want to choose as the Curtin subalgebra, right? Because the rank of a Lie algebra, say G tilde, is the number of mutually commuting generators, okay, you know, which is known as the Curtin subalgebra. Curtin was a great mathematician. He also developed the theory of spinors, you know, so yeah, as well as did the classification of the Lie algebras. So like a huge figure in the history of mathematics. Okay, so we choose our Curtin subalgebra, our CSA, as we call it CSA, you know, to be J3. Okay. Now, let's talk about another operator which we shall need. It's called the Casimir invariant. Casimir, or it's also known as the quadratic Casimir invariant.
Sorry, is this the Casimir from Casimir effect that proves
possibly
the parts of
I'm not, yeah, possibly, I'm not sure.
Okay.
Yeah. Since the spelling is the same, It's probably the same. Or maybe not, because, this is a mathematician and the other one was a physicist, so it's probably not. So quadratic Casimir invariant. So I don't think it's probably not. Casimir is a very common, I think, Polish or East European name. So what is a Casimir invariant of SU2? So before I do that, let me just give you a little bit of background. If you remember, we discussed Schur's lemma. Now, Schur's lemma tells us that any matrix, that commutes with all the matrices, say D of G, of a representation. So meaning that, for all G in G, then that matrix is proportional to the identity matrix, right? Now, it is enough for us to be able to show that if a matrix commutes, or an operator commutes with all the generators, then of course they're going to commute with, that matrix is going to commute with all the group elements, right? Because the group elements, well, if you're just talking about, we are talking about the connected part of the Lie group, the connected part of the Lie group is nothing but the exponential map of the Lie algebra, right? Sorry, we lost the visual. Okay, so is that a statement that makes sense? That if, say, if B commutes with all the J's, then that means that B will also commute with all the finite elements of the group, right? Is that something that makes sense to you? So I hear silence, that means no. So yeah, so what are the finite elements? It's E, I, theta, A, J, A, but this is basically a power series, right? That's the first term, and then you have the second term. Things like that. So now if, of course, every matrix commutes with the identity matrix. But if a matrix commutes with, say, theta A, J, A, then of course it'll commute with any power of that matrix, right? Right, because we know that when we have A, B, C, the commutator, we have, which is A, B, C minus B, C, A, right? But we can also write that as A, B, C minus B, A, C plus B, A, C minus B, C, A, right? So I subtracted this and added this. And the first term is just the commutator of A and B times C. And the third and the fourth term are the commutators of, is the commutators of B times the commutator of A and C, right? So now if I apply this to the case where B, J, A squared, that will give me B times J. So the commutator of Bj and J plus J times commutator of B and J. So if this is 0, and if this is 0, this is 0, right? And you can recur, by recurring this relationship, you can show, it's trivial to show that this is then true. Okay? And therefore, if B commutes with this combination, it'll commute with this whole series, and therefore, if B commutes with just the Lie algebra, it's going to commute with the connected component of the Lie group. Okay? Is this clear? Can you hear me?
Yes.
Okay, but is this clear?
Yeah.
Okay. What about other people?
Yes, sir.
Okay.
Yes, sir.
I mean, I'm very happy to re-explain stuff, okay? Just don't be shy. Okay, all right, good. So why I'm saying this, because there is a very important operator, which is called the Casimir operator, which actually commutes with all the generators of the Lie algebra. And that operator happens to be J squared, which is the three operators J1, J2, J3 dotted with itself. So it's basically J1 squared plus J2 squared plus J3 squared, okay? It's very easy to show that the J squared operator commutes with all the individual J operator, okay, for all A. So what does this mean? This means that the J squared operator must be proportional to the identity matrix, right? Now, J squared is Hermitian, because JA is Hermitian, right? And therefore, lambda, this eigenvalue, must be real. Okay.
So will it also be positive?
It'll also be positive, yes. Yeah, because any operator that can be written as, say, M dagger M, if there's an operator, say, O, which can be written as M dagger M, then this is a positive definite operator. Right, and in this case, J squared is JA, Of course, J is Hermitian, so we can write it like that, right? Okay, so this is very easy to prove that this, you just say, okay, I apply O on some vector, psi, and I take its conjugate vector, the Hermitian conjugate, and that gives me M dagger, M of psi, but this thing is some other vector, say phi, and this thing is just its conjugate vector phi, and this thing is greater or equal to 0. Okay, let's come back to J squared. Now, J squared has an important rule. has an important role in labeling the vector space, Vn, on which, say, JA, J1, J2, and J3 act irreducibly. Okay, so if you take any vector from this vector space, for any vector, well, this is very bad notation. For any vector psi from the vector space on which JA act, J squared will give you lambda psi, right? By definition, right? But not by definition, but by Schur's lemma, right? Okay, do you agree?
Yes, sir.